All right, we're going to do some examples of taking the derivative of e to the u, and our last goal for this unit is going to be to find the antiderivative of e to the u, which we'll get into soon. All right, so from our discussion in class, we discovered that the derivative of e to the x is itself one of the beauties of an exponential with a base of e, why we have that as the natural base. And then we extended our understanding to say that if we have the derivative with respect to x of e to the u, where u is a function of x, then we can take the derivative using the chain rule, e to the u times the derivative of u with respect to x, or you might want to just write e to the u times u prime. You can say e to the something times the derivative of the something, whatever it might be, but it's the chain rule that's at play there. So what we have for you is a set of 5 examples that we'll go through using this new rule. And the way this video is going to work is I'm going to introduce you what you should start with, then I'm going to ask you to pause the video and try, and then we're going to compare answers. So for the first problem, we have f of x equals x squared times e to the x, which means that we should be applying the product rule for this problem. And then the second one, we have g of x equals e to the x plus e to the negative x divided by 2. And I'm going to say you might want to jump to the quotient rule, but actually remember dividing by 2 is the same thing as multiplying by 1/2. So I think a good first step here is to think about g of x as 1/2 the quantity e to the x plus e to the negative x, and then take the derivative. So go ahead and pause your video, try these 2 examples for yourself, and then come back and check your answers. Pause now. But really, pause for yourself and try. All right, taking the derivative, we have the first times the derivative of the second plus the second times the derivative of the first. And then I went through and I pulled out a greatest common factor. So each one of these terms in blue has an x and has an e to the x. Well, what's left from this first one when you take out x e to the x is just x. And what's left from this second term when you take out e to the x and x, you're left with a positive 2. And you might be saying, okay, but like, why would that be necessary? Well, think about follow-up questions that are often asked about the derivative. Oftentimes we set the derivative equal to 0 and consider where it may be undefined to find critical numbers. Seeing it in this form is a true mathematical answer, that is the derivative. But seeing it in this form makes it easier when we do set the derivative equal to 0 to go through and find the zeros, right? Either x is 0, e to the x is 0, which will never happen, so we don't have to worry about it, or x plus 2 is equal to 0, and we would get a critical number of negative 2. Okay, so the only reason I show you this form is just the cleaned up part to potentially answer follow-up questions. For the second one, g prime of x, 1/2 just hangs out in front as the constant. The derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times the derivative of the exponent, which would be negative 1. Cleaning that up a little bit, I just think instead of saying times negative 1, it makes sense to pull that negative out in front. So there's your g prime of x, final answer. All right, example 3 and example 4. Example 3 says solve for dy dx, implicitly defined curve. So we're going to need a product rule between these two and a product rule between these two, and then we're going to isolate the dy dx. This one, write the equation of a tangent line for m of a is equal to this mess at a equals 0. To get you started there, I'll remind you that the equation of a tangent line should be y minus your output equals your slope at, in this case, 0. So this we want to find m prime of 0 is what's going to go in there. And what's going to go in here is just m of 0. So pause your video, try these 2 for yourself, and then unpause and see how you did. Pause now. All right, let's talk through this one first. So the stuff in green required a product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. I wrote the 1 just so we could see it. Then the stuff banded together in purple needed another product rule. There's the first times the derivative of the second plus the second times the derivative of the first, Remember, dy dx is necessary because you're taking the derivative of a function y as it relates to the variable x. And then the derivative of 0 is just 0. Our next step then is we want to isolate our dy dx. So I'm going to keep this term that has a dy dx on the left side, and I moved everything else to the right. Now, you might have said, instead, let me move the 2e to the x dy dx to the right and keep everything else on the other side. Doesn't matter, we just might have a little bit of a difference in, I have my negatives across the top. You might have had positives across the top and a negative on the bottom. That's totally fine. I also chose to simplify and say each one of these things has an e to the x in it. So I'm safe to cancel out that function of e to the x because e to the x will never be 0. So I'm not dividing by a 0 when I cancel those out. All right, next one required a little bit more heavy lifting, right? We're looking to write the equation of a tangent line, which means I need a point and I need a slope. Well, my point has an input of 0, and then I needed to find the output. So in goes 0 to m, and out came 1. So I got my coordinate point of 0, 1. The next thing I need to do is take the derivative of m. So I rewrote m by bringing this e to the 2a up top. Okay, so I just made that e to the negative 2a, just so that when I take the derivative, it becomes a little bit nicer. I can get rid of this screen there. There we go. So this is just m of a. I have not done any calculus yet. This is where the calculus kicks in. So the 5 is just hanging out. This is e to the negative 2a times the derivative of the exponent minus the 4 just hangs out, e to the a squared plus 2a times the derivative of the exponent, right? It's e to the u times the derivative of u. The next thing that I did is I substituted in 0. So 5 and negative 2 made my negative 10 e to the 0 minus 4 e to the 0 times 2 times 0 plus 2, which is 2. Altogether, I come up with negative 18. All right, this next one puts together a lot of important information. We are trying to find the points of inflection. Well, by definition, a point of inflection is a max or a min on the derivative, which means we're looking to set the second derivative of q, and b is our input instead of x, just testing your knowledge of variables here. Q double prime of b needs to be equal to 0 and have a sign change. So what you're going to do here is you're going to take the first derivative, then you're going to take the second derivative, set that second derivative equal to 0 or consider where that second derivative may be undefined, and check to see if you have a sign change. This is a tricky one. Pause the video, try for yourself first, then come back and listen to my explanation. So again, take the first derivative, you'll need a product rule, clean up your result, then take the second derivative and set that equal to 0 or consider where it may be undefined. I'll see you back here in a few. Pause your video now. All right, let's look at this mess. So for the first one, I just did the product rule between these two. So first derivative of the second plus the second derivative of the first. Then I cleaned stuff up and I rewrote it and factored out the negative b, e to the negative b, just like I showed you in example 1, that we might want to have things cleaned up when we have a follow-up question. So this then, when we take the second derivative, requires a product rule. So I have my first times the derivative of the second plus the second times, wait for it, the derivative of the first. Well, the derivative of the first needs its own product rule. Like, this is tough. Okay, but you are strong. You will persevere. You will use the product rule and be great. So then what I did is I just cleaned stuff up again. Negative b, this red and green together makes this purple. Then I took this green and I distributed it, right? Do a little FOIL action. Then once I have that, so this is the blue distributing to each and the yellow distributing to each, then I combined like terms. So this first one, and this one were all the same type of term. They're like terms, combined to be negative 4 of those things. Then the b squared e to the negative b is its own term, and this 2 e to the negative b is its own term. Then I factored out an e to the negative b. Oh boy. And now I've got this condensed to here, and I'm supposed to consider where this is 0 or where this might be undefined. Well, take a second and catch up for yourself. Pause the video if you need to catch yourself up. I know it's a lot of notes, but think about what's happening in each step. Look back at your work and compare and contrast. Don't just take mine when you pause the video. Think for yourself. There's plenty of time. All right, now that you've paused and you've had time to think about it, let's set this equal to 0. So that means that 0 is equal to e to the negative b, or 0 is equal to b squared minus 4b plus 2. Then we also have to consider where might this be undefined. Well, e to the negative b is just the exponential decay model. That's never going to be undefined. And then b squared minus 4b plus 2 is just a parabola. That's never going to be undefined. So we don't have to worry about that. E to the negative b is never going to be equal to 0 because of exponential decay. This one, I can't factor this. So am I going to use the quadratic formula? You bet I am. So this time we don't have x, we have b. b equals opposite of the b coefficient plus or minus the square root b squared minus 4ac divided by 2a. Okay, well, oh boy. b equals 4 plus or minus the square root of 16 minus 8 is 8 over 2. So 4 plus or minus 2 root 2 over 2. b is equal to 2 plus or minus the square root of 2. We can put these on a number line to confirm. I'm going to let you know that these do in fact count as points of inflection. So we're going to have 2 plus the square root of 2 and 2 minus the square root of 2. A point of inflection is not complete without a y value. How do we get a y value? We always go back to the original, which was this b squared times e to the negative b. So b squared times e to the negative, that should be squared, negative b, and b squared times e to the negative b. And those are your points of inflection. And are they a mess? Yes. Yes, they are. If you took the time to plot these on a number line, remember you would label your number line as q double prime of b, and you would have 2 minus the square root of 2, 2 plus the square root of 2. You would try to input these things into your second derivative because you're doing a second derivative testing for extrema. So this is, testing for points of inflection. Whew. This comes back positive, this comes back negative, this comes back positive. So we have concave up, concave down, concave up. This last problem is a lot, okay? Big takeaway from today, though, is do you understand that every time you come across e to the negative b, that derivative comes back as e to the negative b times the derivative of the exponent. That's the big takeaway. The little intertwining of AP review is the idea of how do you find points of inflection. Or, in example 4, how do you write the equation of a tangent line? Again, summary, the derivative of e to the something is e to the something times the derivative of the something.